This one, let's find out what are the conjugate bases after the most acidic proton goes away. This is the most acidic proton, that's the most acidic one, this is the most acidic one. On this side, that one, this one probably have equal chance, but let's just take the same one within it. Anyway, so when you draw the conjugate bases of them, this proton goes away, you're going to have oxygen negatively charge it. When that proton goes away, you're going to have a sulfur negatively charge it. When that one goes away, you're going to have a nitrogen negatively charge it. When that one goes away, you're going to have a carbon negatively charge it. And then all four of them will make a resonance structure. That will make a resonance structures. So this negative charge goes to there, right? By come in double bonds and single bond with the negative charges. That's the same thing. You're going to have a resonance structure same way that comes in, that pops out. You're going to make the resonance structures. That also make a resonance structure. All four of them, they all can make a resonance structure. Then how are you going to sort it out? This one's a little difficult compared to what we talked about because it's not just a single concept that you need to use it. You've got to combine multiple concepts together. Even though making resonance structures doesn't really become effective because all four of them do it, right? But anyway, let's talk about things one by one. These resonance forms, other than their chemical resonance structures, these forms have all of the oxygen becomes a negative charge, all same. So there's nothing we can tell the difference between by these resonance forms. So we need to talk about these forms. That's where the differences are. Oxygen being negatively charged, sulfur being negatively charged, nitrogen being negatively charged, carbon being negatively charged. We got different atoms having a negative charge. So then which factor do we need to use? Do we need to use electronegativity, or do we need to use sign? Okay, you're kind of making up your mind which one I need to go, right? What I'm going to say is you probably need to use both, right? Because you may have to make a group. Let's say this way, oxygen and the sulfur, they are on the group 6, right? Sulfur is right underneath of oxygen that we just talked about example before. Sulfur negatively charged is better than oxygen negatively charged, not by the electronegativity, by the size. Right? The same rule goes the same way. Sulfur being negatively charged makes it more stable than oxygen being negatively charged. So if you want to sort it out between these two, you gotta use a size because they all belong in a different row in the periodic table. But if you're comparing this oxygen, nitrogen, carbon, you gotta use electronegativity because size-wise, they're the second element. They're going to have the same number of electrons. The size about the similar. Then what you need to use to sort it out between those three, except that one, those three must be the electronegative. Oxygen being more electronegative than nitrogen, nitrogen is more electronegative than carbon. So depending on what you're going to compare with, you got to use a different factor. So between these two, you need to use a size. If you're going to sort the other three, you must use electronegativity. Thankfully, we have a dot one common. You can place them. So let's talk about first thing is yes, this one is more stable than the other one because of the sulfur being negatively charged, makes it bigger size. It can handle anions better than oxygen. So if you only compare these two, that one's going to be more acidic than the other one. That we can say. Excluding this one, compare these three, those three. Which one's going to be more stable among this one, that one, this one? Then you need to use electronegativity because we're going to make the same size anion. So oxygen negatively charged is better than nitrogen negatively charged. So this is a more acidic than more stable than the other one. And that one's going to be more stable than that one because it's carbon negatively charged. So if you just think about that, that's going to be the better than this one, and this is better than that one, so this should be better than all the other two, right? This basically two things comes together, then you can make a ranking. This being the most stable one, that makes this one most acidic. That's a second acidic. That's a third one. That's a fourth one. So you need to be able to put things together, and if there's some common one, then you can probably make a sorting based on that. So those are something like you gonna have a little bit more headache because it's not straightforward, not a one concept you need to use. You gotta do the more than one concept together. And those type of things are something that will probably be a little more difficult. So you've got to practice. And it's not that difficult, you can figure it out. All right, moving on. There are lots of examples you can do. I'm probably going to stop sometime, but you should do a lot of practice at home. All right, there's 5 molecules there. Well, our task is to sort the molecular bases acidity. So we're going to figure out what's going to be the conjugate base, how stable they are, those same thing. So that molecule, what's the most strong most acidic hydrogen? The hydrogen and that oxygen. So that makes a conjugate base of this. This is a sulfonic acid. When this proton goes away, you've got oxygen negative to charge it. And you see that one can make a lot of resonance structures. That is a proton goes away, you've got the dark side, negative charge oxygen, but that's it. We have no more resonance structures, right? And that's basically the same thing as a carboxylate. We discussed that before. There's another carboxylate. Anyway, you got to recognize most acidic hydrogen and then start drawing the conjugate bases. After you have done that, then you need to talk about the stability. But not just talking about, you got to come to group them together. Right? Make a ranking something you can do, and then make another ranking something you cannot do later. So first of all, the resonance structures, it is one of the big factors. It makes a big difference. This is a sulfonic acid that makes 3 resonance structures. Right? That's something that we cannot just ignore. If just a 3, you may think that some you cannot even make any, like this one. That one, I would say probably least stable along those 3 because of 5. Because this one can make 3 resonance structures that cannot, but then the other 3 can make a resonance structure like this. All 3 of them. So anyway, so these can make a resonance structure. So that can make a resonance structure the same way. This one can do. So these have the 2 resonance structures. That's 3. That is none. Which one's the most stable one? I would say this one. That becomes the most stable. That makes the most strong acid. Which ones are least stable? This one, because that does not make resonance structures. That should be the least strong acid. That is an easy part to figure out. Now the question goes, those 3, these are the same type of resonance structure. Carboxylic acid becomes carboxylate, becomes another carboxylate by making resonance structures. So that makes the same thing, this makes the same thing. So how can we figure out which ones are more stable than the other, right? I mean, obviously, they're not having the exact same structures. There is a chlorine there. The chlorine is an atom that has a higher negativity compared to carbon, and it's a little higher, but it's a higher. So there's electron withdrawing groups. It's full electron density from that oxygen. So that can help out. If you have electron withdrawing groups, electron donating groups in the structures, and change the electron density through the bond, that is called as an inductive effect, right? We talked about that. Chlorine, being an electronegative atom, it pulls electron density from out, so this oxygen doesn't need to handle 100% of the charge by itself, and obviously together with the other oxygen. So chlorine can help you out. So this is better than that one. Between these two, having chlorine makes it more stable than without having it, right? So those 2, if you compare those 2, they should be better than that. What about this one? There's a chlorine too. So these 2 should have the same acidity. What matters is where they are. Chlorine is on this carbon right next to this carboxylate functional groups. That one chlorine is here, is further away. It's pulling it out, but pulling it out from the close proximity should be better than pulling it out from the farther away. Right? Distance between these negative charge species and where they are, that could matter too. This chlorine closer to the carboxylate make a bigger impact compared to the chlorine further away. So it's better than still having it without not having it. But that one is worse than that one because it's further away. It's kind of very intuitive. So if you consider that, yes, this one's the most acidic by having a most number of resonance structures. That's the least acidic, having no resonance structures at all. It has to have 100% charge by itself. But among those three, the chlorine electron withdrawing groups in the close proximity should be the better than the other one. And then having none is probably least among those three. So you probably have to sort things out. Sometimes it's concept, sometimes the other concept, sometimes there's fine differences in the structures, and that's what you need to pay attention. And voila, that's how you solve this problem.